So this is working or not? All right. So great, everything's working. Well, I'm actually eager to tell you about the new stuff that I've discovered, and it's quite fresh, and it's about the approximation of AIXI. Well, it's not fully developed yet. It's just some results, some ideas. Some are fully developed, some are in progress, others are just vague. But I would nevertheless like to share it with you because I think it's cool. Okay. So how is this working now? I have to point to this. To this guy? No? Down. Down. Okay. All right. So Markus Hutter, as you know, has developed the theory of universal intelligence, and it has been shown that the AIXI agent that he has developed there is a universally intelligent agent that has proven to collect the maximum rewards in a wide range of environments. It's Pareto optimal in that sense. However, if you want a practical theory of AGI that you're going to go ahead and implement, there are many obstacles to that. And I've recently talked to Richard Loosemore, and he said, well, AIXI is not a theory of AGI. AIXI is an abstract piece of unimplementable fantasy, which is, in some sense, he's right. And I agree. It is, as it is, unimplementable, and it's quite abstract. So, nevertheless, I see it as a challenge, not as an obstacle. Pei Wang has repeated the assumption of insufficient knowledge and resources, actually, and I think it's a very important thing to consider. And so how can we consider that assumption, take it into account, and still make AIXI work? Because it's actually a beautiful mathematical theory. So what's the strategy? How can we alleviate the sources of its intractability? The idea is to make assumptions, right? That's how you get more efficient. You make assumptions. But you want to make such assumptions that don't make it a narrow system. That would be not interesting, right? You want to make an assumption that are generally true for the universe we live in, but not necessarily universally true. So universally true would mean for all mathematical objects or whatever, or data strings. And for our universe means for the data that is actually generated by the physical laws that we live in. And as it turns out, you can find actually assumptions and find mathematical formulations of them that reflect those properties. And we shall embark on that. So let's refresh a little bit what AIXI is about. So you have, it can actually be expressed in a single formula. So you have discrete time steps from 1 to k. K is the current time step, and then you look into the future m's time steps ahead. So it's an agent framework, so at every time step you get an observation and a reward, and you make an action. That's it. And what you have done, if you are at time step k, and you have m time steps before you, you don't know what the future will be like, so you consider all futures that are possible. So these are, so since the observations and rewards and actions come from finite sets, you can take the set of all combinations is also finite, so you can consider that set. Now it's of course majorly impractical, and that's the point 4 here. That's the big trouble, exponential number of them. So now let's suppose you have this past and one such future. What you do is to look for programs that you execute on the universal Turing machine that takes the actions and compute that history plus future. And you consider all programs that exist and that compute it. And there are infinitely many of them. And you weigh them with the length of the program. So it means the short programs that you find that can compute your history plus future have a big weight. That's the Occam factor here. So this guy here is called the Solomonov prior, by the way. And this is a sense of a certain probability, actually. The probability that the history that you have observed happens, and plus the future that you're currently considering. And as you see, there are also rewards here among the observations. So you can, the future that you're currently pondering about contains also rewards. And you take the sum of them and multiply it by probability is actually the expected reward. And what you have here is essentially the maximum of the expected reward. That's all AIXI is. You have to iterate the max and the sum, because that's how you have to do it. But essentially, you pick then the action that maximizes this expected reward according to this Solomonoff-Prior distribution. That's all AIXI is about. So there are a long list of difficulties that everybody is aware of, or many are aware of. It's incomputable. Why is it incomputable? It's because the Solomonoff-Prior is incomputable. It's due to the halting problem, essentially. Programs, not all programs halt, and you never know whether they will. And there are infinite number of programs to induce. The sum over Q is infinite. This is bad. Now, if you want to approximate this and say, okay, let's keep only the short programs and throw away the long ones. This is essentially compression. That's what you have to do. You have to find short descriptions of your data. And, but AIXI does not specify a compression algorithm. So how do you go about it? Next problem, the possible futures is huge. And suppose you have solved even all that. For all futures, you have done this compression, and then you are now then exhausted, and then the next time step comes. K goes to K plus 1, and then what does AIXI says? Do it all over again. do the whole business all over again, and it kills you, of course. And the next problem is you have a high dimensionality, and if you do micro planning, like in little steps, but you want to plan your whole life, of course you cannot do micro planning like this. You have to coarse grain in some sense your life, to have some stages in between that you plan in between. And that will be a major point that I would like to address in this talk. But before, let's look at all those points actually. Can we do something about it? And I would like to argue that we can. So, let's bring it on. What about incomputability? So, it works. Well, actually, there is already a computable version. It's called AIXI-TL. Maybe some people don't know it. T is the number of time you have provided. L is the length of the programs that you can, maximum length that you consider. And Hutter has already showed long ago that it is computable, and it's actually also the optimal agent among those that are also restricted by the same resource bounds. Now, incomputability is also not so bad because the Solomonoff-Prior is lower semi-computable. So it means you can actually construct approximations from below. So you can actually point to an infinite sequence of functions that are monotonically increasing, and that in the limit actually reach the Solomonoff-Prior. So that just means the ideal is never reachable, but you can get arbitrarily close. And that's for practical AI, that's all you need. You don't need the ideal. Who needs the ideal, right? For practical AI, you need something to be good enough. And for good enough solutions, things become computable. And also, the incomputability is also just for the shortest program. But you can find short ones, not necessarily the shortest ones. And as unsupervised machine learning demonstrate, short programs are often good enough because unsupervised machine learning does compression essentially. Like a clustering algorithm is a compression algorithm because you replace all the points you have by the clusters. And you can do that for various examples. So it's not optimal, but it does some compression, and as the success of machine learning evidences, you can build very useful systems, even though you're not optimal, or have not found the shortest. So I don't think it's, and the bottom line of this is incomputability is not such a big problem as it often appears to be, or seems to people. So, but this mark is in brackets, but because you have, of course, need to develop a computable, fast running algorithm ultimately in order to solve that issue. So let's take on the next problem, the infinite number of programs to induce here, the infinite sum. Well, that's actually, hopla. Yes. So, what you have here is, this can actually be solved rather simply. So you have the coding theorem of algorithmic information theory. So it says that the Solomonoff prior, which stands here, the infinite sum can be actually replaced by 2 to the minus of the Kolmogorov complexity of the involved strings. That's kind of profound. This is a profound theory of algorithmic information theory, because this term is actually one of the terms here, sort of the shortest program. So the whole sum coincides up to a multiplicative factor with the whole with one of its summands, with the largest one. And it's not completely unproblematic. There has been a paper by Hutter also in 2003 that examines the predictive properties of this. But you can actually do that. And since AIXI is derived up to multiplicative factors anyway, you can replace it by this. So there you go. You have gotten rid of that infinite sum. So, well, no compression algorithm is specified. Next problem. Well, that's what you know I've been working on for the past years. It's the algorithm on incremental compression. Just a quick overview. What you have is your data string up there, and you search for a pair of functions that reduce the length of that data string. And then you search for a second pair of functions that reduce that length even more. And you do it iteratively, and there are mathematical guarantees that you approach the Kolmogorov complexity actually in the limit. To some precision, yes. So, I'm not going to go into detail here because I've presented it several times before, and you can look it up in the publications. Rather, I would like to focus on what we can do with it when applying to AIXI. So, I said there is no memory update mechanism. You know, you have compressed stuff, you have done all this efforts to find short representations, and then new data comes in. How do you update your representations as new data come in? So, there's a little nice theorem that I could prove, that we could prove in the lab. So let's F be a feature of X. A feature is essentially a function, a little Turing machine that maps the residual description onto X. And you can see it as a property of an object, like the color or so, or the shape. It's a partial description of the object. And let's say that G star is the shortest feature of some extension of X. You got new data Y. Entered, and now you have the concatenation XY, you have to explain. How does it change? Well, you can show that the feature of the whole, the shortest feature of the whole will be bounded by the pre-feature before. Well, the reason is features are not full descriptions. And if you have a property of X, it will be also a property of XY, because you can just map the content of Y into the residual. You can just copy it into it, and that's it. So, intuitively speaking, you have, let's say, you have the color of the ceiling. You have described it, and then look not just at this ceiling, but at the next ceiling, but the color of this ceiling will still remain the same. It will still be a property of a larger world in that sense. And one theorem that is in progress actually, that features, if you pick the shortest features, they appear like atoms of information. So let's say you want to describe an object, and you have little pieces of information, little pieces that describe the object. Then the theorem seems to show that for two objects, if you look at their features, the two features are either completely disjunct or identical. They seem to have an atomic property. Now, if this is true, this means that you can build descriptions made up of a set of atoms. And you can, like a Lego block, you could put them together and have a description. Put the Lego construction apart into blocks, you can combine it differently and you get a different description. If that works out, that would be really beautiful. Because it would turn out that the description are actually discretized into information theoretic pieces. So if this works out, updating a history means the following. So you have the history and a bunch of features describing the history. And then you have new data coming in. So either the new data will have features that are identical to some of those that you already have, so you just throw them away, or they have new ones, that you just put them in your bag. So you have you're going around and collecting those features. You don't have to rearrange them, or you don't have to completely overthrow those features that you already have found. And that's a crucial step in the memory update problem. So you have to, this is again in brackets, you have to specify it how exactly it has to be done, and you have to work out the theorems, but it seems to be working. Now, the exponential number of possible futures. What can we do about that? Well, when you look for descriptions, how should I explain this? Often when we want to predict what will happen in the future, we don't consider all combinations of futures. We use our experience and project that experience into the future. I mean, in the algorithmic way of speaking, you just compute your futures from what you had before. And before you had only the computation of your history, so you do have to change something. But you can show that there are small changes that you can introduce to your features, and the small changes will compute the most probable futures. Why is this the case? Because the most probable futures are those that contain the least independent information. So if I walk like this, and you predict that I will continue walking, and this prediction contains the least new information, because you have already seen me walking here. So the smallest updates to your descriptions compute actually the most probable futures. So you don't have to consider all of them. And that's the intuitive flair behind the theorems. And if you do that, you can just skip computing all the futures. You can just focus on the most probable ones, because those are the ones that will guide your search for rewards anyway. Why is this the case? Well, you see that the length goes exponentially here, while the reward goes only linearly here. So if you have the shortest ones that give the most probable futures, this will give by far the largest factor. So here's the second way how the theory allows to truncate the consideration of all possible futures. So this is the expectimax search tree. So this is your history, let's say BAAB, and you have done some actions, past actions, left, right, right, left, and then all possible ways to make an action, to see an observation, to make another action, and to see another observation. So, and for each of these possibilities, there's this 2 to the power of minus term. And what incremental compression theory now says is, you actually, while doing this compression, you derive upper and lower bound for the complexity. So you make one compression step, you have a lower and an upper bound, and the homograph complexity is somewhere in between. If you make another compression step, the bounds narrow down. Yeah, you see that here. The homograph complexity is the sum of those blue ones plus the last residual. And if you've done just one step, the bound is just from this to this. The homograph complexity is in between. After the second step, the bound is from this to this. So it narrows down. So what does that mean? Here you have to find the homograph complexity fully, if you are fully compressed. But on the way of compressing, you have actually here lower and upper bounds. So at each leaf here, you have an interval where you know, aha, the right value will be in this interval. So, and then, as it will happen, for 2 leaves, the interval may stop overlapping. So because they both narrow down. And then you know, okay, this guy will have higher expected reward than this option. So you can start truncating the expectimax tree before you have even finished compressing. Yeah? So in this option, you have to consider all possible futures, but you don't have to compress all the data for every future. You compress the first step, and then already some possible futures will be truncated. You compress the second step, some more futures will be truncated away. So essentially, you don't have, you are much faster then. And this also has to be worked out how this goes precisely, but this requires the distribution on the lengths of the features, which we don't have yet. But essentially, this should work this way. So, all right. So we have the first 5 points. Roughly, hopefully, I could give you an intuition of how I'm going about this. And let's get to the largest 6 points, which is actually the most crucial one, because it's the high dimensionality of this whole problem that kills your computation essentially. What if we could coarse grain AIXI into a smaller AIXI where there are only a few states? Let's say I go to the door, then I go to another door, and I go to the exit. So in such a space, planning is easy, even with such a cumbersome system as AIXI is. Even AIXI would do it computationally. And so the big question is how can we coarse grain the environment such a way that that we arrive at a description or at some state representation that is relevant for rewards. If we can do that, it's good. For example, there is Jessica Flack from the Complexity Institute in Santa Fe has studied apes that have to estimate fight or flight response. So all you need from your own fighting history with other apes is who is bigger, me or the other ape. and that's most predictive of the reward you get, positive or negative. So this is an example of coarse graining. You ignore all the complex history, only keep what is the size difference, and then you can compute predictions of your rewards. So how can we formalize this? So let's introduce some simplifying notation first. So we had this AIXI expression, where this is the value function here. Let's write down the history like this. Let's call it x. the future will be y from k to m, and the sum of the rewards will be just a fixed function of y. Raw just extracts the rewards from that string. Simple operation. It's just a shortcut. The past actions will be with the over left arrow from 1 to k minus 1, and the future actions I shall just call a from k to m. And if we write that, then AIXI becomes something like this. very concise. Now, this max sum is just a shortcut for this expected max thing. So, what can we do with this? Oh. It actually will show us that we arrive at something like a Boltzmann distribution from physics. And how would you do that? So we have this term, the complexity of a pair of strings. Well, what is it? We just use the chain rule. That's the algorithmic information theory. It's just a chain rule. If you know how to describe x, and you know how to describe y given x, then you know how to describe x and y. And that's the same thing that here we meet our first assumption, actually. Everything before was general. The assumption is that we live in a chronological environment. That means future actions do not influence the past. What a harsh assumption. So we forbid time travels, I'm sorry. And so what you can get here is the future actions can be removed here because they don't influence the past x. And here's the chain rule, just the same thing as here. And don't bother about the x star, it's just, it's just technical detail. It's just the history. So what you have here is now a term that is not dependent on the expected max operation, not dependent on future actions and futures. So you can pull it out, and what you hear is something quite beautiful, actually. What you have is here is a sum of our actions and futures, such that the future will follow most easily from the past, from the history and future actions. So what does it mean? AIXI actually assumes that the world is going to develop in a way that is most probable, that is most easily computable from what was before. Well, let's rewrite that a little bit more. Let's fix the actions that you take and compute the expected reward. Well, that's just the sum over all futures, that's the reward sum. And then we have to normalize it so it's going to be a good probability distribution. So it's just 1 over z, and z is the sum over all futures of this guy. And in physics, it's called partition function. Now I'm starting to use physics terms because it really looks like statistical physics stuff. And now we can rewrite a normalized value functions like this, where this has become the Boltzmann distribution. Why is it the Boltzmann distribution? Well, if you use, instead of complexities, energies, that's what it is, that's how it's called. Or in computer science, it's called softmax. But I want to use the physics terminology because there are a rich comparison between it. So what you have, AIXI is approximately equal to the maximization of expected reward with respect to a complexity-based Boltzmann distribution. Now what does that mean? Let's make a comparison to statistical physics. What do you have here? So this is the usual partition function, where Si are states, combination of states. So let's consider an example. Let's say you have a ferromagnet. And in a ferromagnet, in 2 dimensions, you have spins, like little micromagnets that can point upward or downward. And the combination of spins is such a microstate. This is what they denote by that bracket. And what you do is, then you say, okay, those spins want to have the lowest energy possible. That's when they are aligned in parallel, all looking in the same direction. And that's what you actually get. So this is the sum over all neighbors, neighboring spins, and if they all look into the same direction, +1 or -1, the energy gets lowest. And if they look at the same direction that an external field, if you apply an external magnetic field, if they all look into the same direction, then in the direction of the external field, then the energy is minimized too. Now, in physics, you minimize actually not the energy, or in statistical physics, but the free energy, which is a balance between the average energy and the entropy. So essentially, it says if the temperature is high, you will have all the spins will look in random directions. If the temperature is low, you will get minimal energy states, which means they look all in one direction. And that's what you also, here's a little simulation that you understand. So in high energy above some critical temperature, you get some random stuff, and below you all look essentially in the same direction. And then you have the critical temperature where you actually see some structure. And this will be important for describing of the general structure of the world that is assumed by AIXI. That's why I'm telling you all of this. And let's look at AIXI. What is the parallel to that? Well, we see that the spin configuration corresponds to futures. So you consider all sorts of futures, and you have also a free energy term here, which is a difference between the average complexity, conditional complexity, and the entropy. What does it mean? It appears that the Solomonoff prior has a balance. It expects simple continuations of the future to be more probable, of the past, simple continuations of the past to be more probable, but he also wants many of them, so that the entropy is also higher. So it's a balance between entropy and complexity, entropy maximization and complexity reduction. That's what the Solomonoff prior seems to be doing. And what does AIXI do? Well, the external field corresponds, I'm just mapping the mathematical correspondence now. Well, what variables in statistical physics corresponds to the variables in AIXI? Now, the external field seems to correspond to the history and actions. It is, and the magnetization of the ferromagnet corresponds to average reward. It seems like AIXI behaves in a way, it tries to choose actions to magnetize the environment to give them reward, to give it some reward. And does that at temperature equal 1? There is no temperature here. And I don't know what it means. Maybe it's a critical temperature. And honestly, I haven't wrapped my mind around on the full meaning of this, but there definitely seems to be a parallel. And the curious thing about it is that there's a lot that we know in statistical physics about systems. And now we can take that knowledge and try to map it onto AIXI and see what we can learn actually. Now there's a conceptual difference. In physics, you actually model a specific system, like a ferromagnet. AIXI is a model of an agent that models physical systems. It's a conceptual difference. So that's why in physics, of course, you need to specify the energy. In the Ising model, is one energy distribution. For a different model, it's a different energy distribution. AIXI does not do such thing. It just has this Kolmogorov complexity with general modeling per machine, general way of model stuff. So yeah, that's this parallel. And let's keep moving to the core issue that we actually want to achieve. We want to reduce the dimensionality of AIXI, because then it will become much simpler. How can we do that? Well, in physics, we know techniques called renormalization. That's what you do in physics when you don't want to bother about the details and want only you care about variables that are large-scaled, coarse-grained, that you can actually measure. And in order to extract from a theory some knowledge about this variable, you do these so-called renormalization techniques. So it's known from statistical physics and also from quantum field theory. It's a bunch of complex techniques. But the idea is actually quite intuitive. So let's consider this idea in our intelligent agent context. Let's say you have a maze with rooms and with corridors, and you want to move around. And well, as humans, we say, well, there are rooms, and we can have coarse-grained actions like move to next room or move to the other room, go straight or turn left and go until you meet the next room. So such coarse-grained descriptions we have. And why do we have them? Why don't we have others? How do we arrive at those coarse-grained descriptions? Well, there is an information theoretic notion called conditional independence. Well, what does it mean? Whether you can move from C to any of our other rooms actually depends whether you have arrived at C, usually. So usually the future depends on the past. But if you condition it on a macro future, let's say macro future is you move from C to E. Given that you know that you move from C to E, your micro movements, how you move from C to E, become independent of the past. Essentially, it means if you know where I am, it doesn't matter what has been before, in very vague terms. I did that example with the ape fights. And there is also an exact formulation from 20 years ago called information bottleneck that says extract that part of X that contains the most information about future rewards or about any other variable. If you can do that, then you can coarse grain effectively. And most often it's conditional independence is used for this. Conditional independence is also used when you want to infer, when you do structural learning in probabilistic graph models. You want to have data, you want to derive a graph, and you want to learn that structure. And you want to know what caused what. And you also use conditional independence. So, what we understand from here is that ideally, the expected reward should be invariant under renormalization. So, usually the reward is sparse, right? If I want to get some food at the other room, I won't get any food during making little steps here. That's a big problem in reinforcement learning, right? Everybody is aware of that. And if you map these micro movements and micro states onto a coarse-grained ones, then they're just 2 steps until the reward. Go to the door and go to the food. So, and the sum of the rewards along the lines, both in the macro and in the micro representations, should be the same under renormalization. That's why you renormalize it in the first place. So, now another dense math slide, I'm sorry, but, this is actually shows the steps what you do when you do renormalization. So the idea is that you have this macro future, like moving from one room to the next. And so this is big Y. Small y is all the paths that are consistent with that macro future. So all the micro paths that lead me actually to the food. So let's assume that we have such a micro future. And here, assumption 1 is the consistency. The reward should be the same. That's what I already said. And here's the conditional independence assumption. So the macro future makes the micro future conditionally independent of the history and future actions. Knowing the future that you will have in the macro sense decouples you from what was before and what micro stuff you will do. So this is the expression in terms of Kolmogorov complexity that's independent. You need a coarse graining rule. You need to arrive at the big Y from small y somehow. In physics, it's some average rule. You average over spins, or you take the maximum, or you take just one of them. It's some information destroying operation. And that's given here. There's some constant function that makes you arrive at big Y from small y. Now, the fourth assumption that the macro futures depends only on the macro past. So in a sense, your coarse-grained descriptions should be self-sufficient in some sense. It is another model, just on the coarse-grained level, and it depends on its own macro previous states. Why not? Oh, that small... Oh, okay, you're right. And the thing is that I will talk about self-organized criticality a little later. Criticality means that you're at the edge of chaos. And that's where planning is still possible, but you're not in the completely boring environment where you're just a grid world or so. So you have some complexity, some regularity mixed up with randomness. So, this is, and the other one is just a technical assumption. I don't want to bother you with that. You can ask me afterwards. So, and what you then do is, and I'm not going to walk you through the equations, but essentially, the complexity of the micro elements map to the complexity of the macro ones, plus some additional term. And that's what you want to have. Let's look at the partition function here. Let's say what it happens. And this is the coarse graining operation. You have the sum over all futures are split into a sum over all macro futures and all micro futures consistent with a particular macro future. It's a double sum. So that's what you do in renormalization. You replace the micro sum by the macro sum. And you insert that equation inside here, and you see that you can pull out this macro term. And if this guy remains constant, which is here by the assumption, this is essentially the renormalized partition function. This is the same as here, just with the big letters. So the partition function is essentially invariant under the transformation up to this factor, but this factor will cancel in the next step, which is the most interesting one. Now you have the expected rewards in AIXI. What happens with them? Now, this is the Boltzmann distribution, this is the rewards here. It's similar to this. And when you renormalize it, and again I save you the details, you get just the very same expression like before, just with the big letters. And the constants here cancel. So you get the expected reward in the coarse-grained AIXI. That's exactly what we wanted. We wanted to map the fine-grained AIXI to a coarse-grained AIXI in such a way that you guarantee still the same expected rewards. Which would allow us to conclude that AIXI remains invariant under renormalization given these 5 assumptions. So, yeah, what does it mean? AIXI's dimensionality can be reduced this way. Then you can, of course, repeat that coarse grading procedure. You can do it again. And as far as reward resolution allows it. Well, what does that mean? Well, of course, let's say I move from this tile to that tile. Here I get something sweet. Here I get something bad tasty. Here I get something sweet. And again, I don't want to smooth over all that area because sometimes I get something good, sometimes bad. I want to do fine-grained actions because I want to get the sweet here, avoid the bad stuff here, and get the sweet here. So I do want to control my actions if the reward distribution is not sparse. So I don't want to renormalize further. But if the reward distribution is sparse, for long ways I get 0, 0, 0, and at some point 1, I can say, okay, let's summarize that into one single thing. That's one macro action. Get that reward. So how far you want to coarse grain is actually depends on your task, and you can choose it. And sometimes the details are important for you, sometimes you're not, depends what you get rewards for. And if this way, some data is extracted that's relevant for your reward, and some data is ignored. Now what is this? Well, that's attention. That's what attention mechanisms are about. It's about ignoring irrelevant data. Let me repeat that. It seems that the renormalization procedure has led us to a description of an attention mechanism in AIXI. And this is great because a cognitive function that humans usually have has emerged from our constraints here, from our derivation. Now we can start to understand the algorithmic reasons, the underlying mathematical reasons for attention mechanisms, which we couldn't be able to do before. Well, but the 5 assumptions that I noted have to be fulfilled. And that means we have to live in an environment that is renormalizable, that generates the data that actually fulfills the properties that we have formulated. Well, what kind of environments are those? Well, if the environment decouples on the large scale, if you repeat renormalization over and over, if it decouples means that the states that you arrive at become totally independent of each other. Then it means you live in a universe where there are pockets of independent things and they don't influence each other in any way. It doesn't seem to happen. It seems like whether we zoom into the tiniest microcosmos or the macrocosmos, we always detect structure in physics. That's called scale-free structure, presence of structure. That's why we have many natural sciences, right? We have physics, chemistry, biology. They have all have their own laws describing the world on different levels. So it seems that the environment retains its coupling strength. So it seems to be in a critical state at the edge of chaos. That's what complexity researchers and physicists, they have derived all their fundamental formulas, but they think they have described the whole world. And then they discover that they actually cannot. And then they research complexity. And in terms of how does this complex world come into existence, and they find that probably the world is in a critical state. And it's in a self-organized critical state, because usually you have to tweak the temperature to be critical and in order to retain a system in a critical state. A critical state would be the transition from solid to fluid, for example. And you have to do fine-tuning in the temperature to remain like that. But the whole world seems to be where the critical state is an attractor. You don't need fine-tuning. So if the world is actually in a self-organized critical state, I mean, and there's a whole bunch of literature on this, it's a whole world, then our renormalization assumptions may apply. That's the actual idea of it. So maybe it's those properties of the universe that make our assumptions true, and then we can go ahead and mathematically formulate that class of environments where those assumptions are true, and say, okay, for this class of environments, AIXI is renormalizable, and we can go to coarser states. So, another mark in bracket. All the details have to be fleshed out, but hopefully I was able to get across the idea. So, let's move to the conclusions. So the troubles of AIXI are not intractable. This is hopefully that I managed to convey. The first steps have been made. Here is the list of the assumptions that we have made. So for incremental compression, for it to work, you have to assume the existence of features or properties. Oh, that sounds very harsh assumption. Well, we take it for granted that all the objects that we have partial descriptions or have some properties. But in the universal set of strings, it may not be true. But if we make that assumption, we can increase the compression process. Chronologicity, okay, we exclude time travel. And we have structural on all scales. That's what the renormalizability was about. And locality that I haven't talked about, but actually in order to discover regularity, you shouldn't have to travel to the next galaxy. So the pieces of the world that actually have to do something with each other have to be nearby, both in time and space. Otherwise, well, you won't be able to deal with it. And that's another assumption I have not yet incorporated, but that's something I'm planning to do. So you see, there are a host of assumptions that you can actually make that makes AIXI will not be a universally intelligent agent, but maybe a generally intelligent agent in our universe. So I've talked about William in the morning today. It demonstrates a little bit of practical success with the incremental compression stuff. So I'm serious with getting the nitty-gritty of programming that stuff into a practical system, because I don't just want to do theory, I want to do both. And there's an intriguing possibility: what if the human cognition is some version of a resource-bounded AIXI? We've already discovered, well, maybe the attention mechanisms actually emerge from that resource-bounded AIXI formulation. I've actually worked through a whole textbook on cognitive psychology, experiment by experiment, and looked whether I could explain that experiment within the current theoretical framework. And it actually fits really well. I mean, I don't have the time to go through it. I've already written up 40 pages of actually writing out the details of the experiment and looking how it matches with the theory. And yes, you can talk about iconic memory, short-term memory, long-term memory. What are the algorithmic reasons for those cognitive functions to exist? Whether are they necessary or just a byproduct of our particular evolutionary niche? Or whether generally necessary in a resource-bounded intelligent agent. You can actually tackle those kind of really interesting questions. So yeah, and I need help. Please. It's a hard job to do, and yeah, I hope I could inspire you to join or to work along those lines. So yeah, thank you for your attention.
Thanks, Arthur, for a very interesting deep dive into AIXI and our well-deserved break starting now. Hopefully we'll resume soon on time because we're about 45 minutes slightly behind, but have your coffee. And service announcement, if you're doing a poster, please, you can set up your poster at the back of the room. After the break, we'll have two more sessions in the panel, and then we'll dive into the posters. All right.